Without further ado, let's start. So I suggest we just go alphabetical order. So we're gonna have like 15 minutes brief talk or reflection by Vincent on space, time, and quantum mechanics.
Yes, thank you. I'll try to share my screen. Good. Can you all see my screen? Yeah.
Yeah.
Very good. Thank you.
Yep.
Yeah. The aim here is just to make a few comments in view of the roundtable about the interactions between work in quantum foundations and space-time physics and gravitational physics. From the discussion we just had, I think it's already well ongoing, but still, I think there are fruitful possible interactions here. So the aim here is try to highlight and encourage in a way potentially fruitful interactions between quantum foundations and space-time physics, where by quantum foundations I understand really in a broad sense interpretational work about the meaning of quantum mechanics, about and also more operational work in quantum foundations. So kind of a broad understanding of quantum foundations here, and space-time physics like relativity until also including work in quantum gravity and research programs in quantum gravity. There is when I raise this kind of questions, there is often a kind of reaction and immediate worry, saying that looking for interaction between quantum foundations and space-time physics is premature in a sense, because there is no well-established common, typically quantum gravitational framework to where these questions can be discussed. So some people might not be willing to take lessons typically from possible insights from quantum gravity until there is a coherent, consistent, well-established theoretical framework. But of course, it's clear that there is a straightforward reply, that there's an intuition that even if there is no such common framework here, still these two contexts can nevertheless be mutually enrich one another. And I'll give examples how quantum foundations issues can benefit from general relativistic insights, but also it goes in the other directions, that relativity and quantum gravity may also get fruitful insights from work in quantum foundation. Now, the general strategy, of course, is to consider issues in quantum foundations, again, in this broad understanding, in the light of space-time and gravitational physics, and vice versa. And here I'll just make very brief comments, quick comments about the notion of local variables, central to many works in quantum foundations, and quantum correlations. In a way, along the lines of Carlo's talk to some extent. You're very familiar with this notion of local variable from John Bell. So those elements which might correspond to elements of reality, to things which exist. So really in a philosopher language would be the ontology, in a sense, whose existence does not depend on observation. You all know this is a reaction to this notion of observable in the theory. So he introduced this notion of variable, which correspond again to the notion of ontology of the theory. And of course, the aim here is to introduce for him the notion of local variables. So really these elements of reality, which in his words, elements of reality which can be assigned to some bound space-time region. That's central element for him in his work, in his foundational work. And so here we see that local Beables, at least in John Bell's work, but also in contemporary quantum foundational work, not all quantum foundational work, of course, is a kind of central conceptual tool in quantum foundations. But also for work on the more conceptual and interpretative side, local Beables are also sometimes taken as kind of ontological bedrock for several realists, strong realists, approach to quantum mechanics and also quantum field theory. For instance, the well-known so-called primitive ontologies approach to the theories like Born mechanics, not the kind presented by Antony, but more the one defended by Detlef Dürr, Tanguy, and Goldstein. But also in the dynamical collapse theories like GRW with this supplemented with the mass density or flashes. So these kind of theories which rely on an ontology of local Beables. But then we see that there is a kind of obvious, straightforward tension with between this notion of local Beable in this explicit sense and the dynamical nature of space-time as described in a quite naive geometric understanding of GR, of transitivity, in the sense that there is no fixed space-time background. And we can ask just the obvious question of when we are looking for local Beables, so local Beables with respect to what? And if we are this can translate in very straightforward way where we're looking for local Beables for the gravitational or metric field in this geometrical understanding of transitivity. This might be difficult. In a sense, this also translates in very concrete difficulties related to the so-called quasi-local program of trying to characterize purely gravitational objects like black holes in relativity. So trying to characterize these gravitational objects using only local notions. So in the terms of relativity, it's quasi-local notions leads to difficulties precisely because of in a way because of this background independence. And also another example, mass and energy in a general relativistic spacetime cannot be unambiguously assigned again to some bound spacetime region in Bell's time within relativity. Of course, there are global notions for isolated systems like ADMS and so on, but in general there is no unique quasi-local notion of mass and energy in GR. So again, these are kind of insights from a well-established physical theory that there is a tension here with the notion of local Beable, and maybe there is something to be gained from these considerations. And when we move to quantum gravity, it seems unlikely that things will get easier for the notion of local Beable in the quantum gravity context, especially in these approaches where the standard space-time structures just seem to be absent but rather emerge at some high level. So the upshot here seems to be that it doesn't seem appropriate to ground one's ontology on a notion like local Beable that is in tension with central features of a well-established theory like relativity, and also certain research programs in quantum gravity. But again, this open also interesting open avenues. Maybe Bell's insight here can be preserved or generalized in some relational way. And for instance, within Carlo's approach to quantum mechanics. But yeah, this is something to be discussed. And now, just a few comments on entanglement or quantum correlations more generally. Also here, there is tension with the traditional separable spatiotemporal picture as defined by Einstein or the philosopher David Lewis. And there is also strong indication that this is a robust, of course, robust feature across many different quantum theories, kind of characteristic trait of quantum mechanics as said by Schrödinger. If we move to quantum field theories, there are very interesting results using algebraic methods in the algebraic approach to quantum field theories. That's in a way, entanglement is more entrenched in quantum field theories. There's these results, there are many different results, but about the kind of generic valuation of delta inequalities in quantum field theory. And also at the level of quantum gravity or certain research programs in quantum gravity, entanglement also play an important role there. I'm referring here, for instance, the kind of gluing role of entanglements in loop quantum gravity or in group field theory. There is also this famous Ryu Takayanagi formula in the holographic scenario in ADS-CFT duality, linking somehow entanglement with distance. So what is interesting here is that now there's work of kind of set of conceptual interpretive tools that have been developed to understand entanglements and quantum correlations at the level of standard quantum mechanics. And these can be now fruitful in the quantum gravity case, where again, space-time structures may be absent. There are again various different tools, and they're not necessarily tied to a particular interpretation of quantum mechanics. In a way that they cut across different interpretations, of course, realist interpretations, but they again might be useful, fruitful in the context of quantum gravity. And one example is a kind of structural realist or relational understanding in a broad sense of entanglement or quantum correlations. And these kind of understanding might help to understand, to characterize a non-fully spatiotemporal level as described by a certain approach to quantum gravity. So there's just examples, but there are other conceptual tools like holistic approaches or modistic conception of entanglement. And here again, it might be fruitful to look for interactions between these interpretative tools and the quantum gravity setting. Now, just briefly, I'll just raise a few questions for discussion. Then I think it would be interesting to ask how, to what extent quantum financial work can be relevant for understanding of space-time and for quantum gravity, and vice versa. How and to what extent the general relativistic understanding of space-time and the insights from quantum gravity can be relevant for quantum foundation work. And here, I mean, these questions not only target to the various realist interpretations of quantum mechanics. So it's not only about developing the pilot wave or the interpretation of quantum mechanics in the quantum gravity context, which is very interesting, as we've heard before, but also I think these are interesting questions for foundational work framed, usually framed in operational or device independent or information theoretic terms. I think I really invite people in the audience and to try to think about to what extent their work, framed again in operational terms, possibly can be fruitful for understanding space-time or for the context of quantum gravity. So these are typically topics I suggest for the roundtable discussion. Thank you.
Thank you. Okay, so now we have again Carlo Rovelli. If you prefer, Antony can go first. I mean, like, but he's not so strict.
I don't mind. I don't mind. Carlo?
Carlo, you're muted.
Antony, go first. It's okay.
Want me to go first?
Yeah.
Okay. Then we have Antony Valentini again.
Hang on, let me just share my screen.
People are bored to listen me talking, so let's get more variety.
Okay, so, well, look, so I understand the idea is just to maybe throw out 2 or 3 thoughts, maybe stimulate some conversations. So I think that this will be quick. So I'd just like to make 3 comments, and they're all related. One common theme is the wave function in quantum gravity. So here's one. Whoops. Hang on. Let me go to full screen. Okay, so one comment is it just like to, I mean, there's been a debate going on for a while about whether, I mean, this is a debate within pilot wave or de Broglie theory or Bohmian mechanics, about the nature of the wave function. Is it a physical object or is it, so sorry, can people hear me?
Yes,
Hello?
it's fine.
Yeah,
Yes, yes,
okay.
we can hear you.
Okay, good. Sorry, I'm just not used to this. So, you know, there's been an argument by Durr, Goldstein, and Zangi that the wave function in de Broglie should be law-like or nomological. You know, part of their argument is supposed to be related to quantum gravity. The idea being that somehow in quantum gravity, the wave function of the universe should be unique. There's just one solution to the Wheeler-DeWitt equation. There's also an argument that somehow the wave function of the universe cannot be controlled. And together, this is supposed to, from this, we're supposed to draw the conclusion that, well, the wave function of the universe is really law-like, a bit like the Hamiltonian or the Lagrangian for the universe. It's not a physical thing. It's something I've critiqued in the past. I mean, just and actually so have Brown and Wallace. I mean, one point is that, look, actually, if you look at quantum gravity, there are many solutions to the Wheeler-DeWitt equation. There are many different kinds of universes, different kinds of situations that we could have that are described by different Wheeler-DeWitt wave functionals. So even though the Wheeler-DeWitt wave functional is in some sense static, time independent, it is a contingency. And the real issue, you know, what separates something that is nomological from something that is a physical object is part of it. It's not just about whether it's temporal, whether it depends on time. It's also about whether it's contingent. Did it have to be that way? Could it have been different? And in quantum gravity, well, the Wheeler-DeWitt wave functional could take many forms. And this idea about, well, you can't control the wave function of the universe. Well, you know, you can't control the intergalactic magnetic field. You can't control the overall space-time geometry of the universe. But our understanding is that those things did not have to take the form that they have. They're not, and what we mean by that is that they're not determined by physical law. There's a certain underdetermination or contingency. And that seems to be part of our understanding of these things as they are physical things that are out there in the world. They take the form that they happen to take, and they're not laws. So, you know, on that sort of basis, I think we have to say that psi is a physical object, even in de Broglie theory, even in de Broglie quantum gravity. Second point I'd like to throw up is against the idea that there is a universal Born rule measure. So again, this sort of feud that's been going on for decades now between myself and the Bohmian mechanics school. I think that the situation changes a bit when you think about quantum gravity. So just briefly, it's a straightforward theorem in de Broglie theory that if you have a big psi, capital psi, for it could be the universe or just some very large system, that if you have a psi squared probability for the large system, when you then extract subsystems, you can derive little psi here is the wave function for the extracted system. Basically, if you have the Born rule for the big system, then when you extract subsystems, you get the Born rule. And this is just fairly straightforward to show. And it was shown in a paper by myself and also by Durr, Goldstein, Zangi. But the way we viewed it is very different. So my purpose in looking at this simple theorem is that, well, my idea was that relaxation for a large system, it could be the universe or just a large system, or would imply the Born rule for subsystems. Whereas Durr, Goldstein, Zangi, the way they look at this is that, well, there's a Born rule typicality measure for the large system, which then implies the Born rule for subsystems. Now, I've always thought that, look, this is just circular. You're assuming the Born rule for the universe, and from that you derive the Born rule for subsystems. And Goldstein-Zange will retort that no, our Born rule for the universe is a different kind of thing. It's a typicality measure, not a probability measure. And I would say, well, what's the difference between typicality and probability? I see no serious difference. And we've gone on and on and on about this. Anyway, so what I want to just a recap of this debate that's gone on for a long time. Quantum gravity, it seems to me, changes things. As I said in my talk, I think there's strong evidence that, well, there is no underlying Born rule in quantum gravity. If you look at the Wheeler-DeWitt wave function, I mean, even in, within standard quantum gravity, most people would agree that what's called the naive Schrödinger interpretation is indeed naive. So what I would say is, if you look at this from the point of view of quantum gravity, if your wave function for the universe is a Wheeler-DeWitt wave function, in other words, a solution to the Wheeler-DeWitt equation, well, there is it's not normalizable. There is no well-defined probability or typicality measure. So I would say that this typicality argument that the Bohmian mechanics school gives, I mean, not only is it circular, but here it cannot even get started. There's no typicality measure that you can begin from in quantum gravity. I still think you can derive the Born rule for subsystems by this emergent semi-classical argument and with relaxation and so on. But anyway, so here's an example, whereas I think in the introduction, Vincent Lamb was saying, how does quantum gravity, how can it impinge on quantum foundations? I think here's an example. I would say that the typicality argument cannot even begin. Briefly, a final thing, my third point I'd like to throw out there, and this is more just a general question about quantum gravity, is, as I said in my talk, while the problem of time in quantum gravity is hugely contentious, and as I said, you might look at Edward Anderson's book of over 900 pages, where there are literally dozens of different approaches to the problem of time, all with their advantages, disadvantages, a very contentious field. But most people agree that the naive Schrödinger interpretation that was used by Hawking in the 80s is really unworkable. And the key point about it is, well, it's psi squared, the Wheeler-DeWitt psi squared is not normalizable, is not a probability. Question I'd like to just throw out there for maybe people to think about is, well, why not? Why is it that in ordinary quantum mechanics, I can take the wave function and I can take the modulus squared and use it as a probability. I think it's fair enough to Hawking that working on this in the 80s, it seemed, well, why not just do the same thing? And it turns out it doesn't work. Why not? So a common answer in quantum gravity circles is that, well, the reason it doesn't work is because the 3 metric somehow contains time. Which then, of course, leads to other issues. For example, if you take the scale factor of an expanding universe as a time parameter, what happens? The universe expands, recontracts. Well, anyway, that's one common answer, which then raises other issues. An answer I've suggested here in my talk is that, well, maybe it's not a probability simply because we have to get used to the idea that there's no Born rule equilibrium state in quantum gravity. And there you go. That's it. That's just these three things I wanted to raise. So I'm going to stop my share, and that's it. Thank you.
Then Carlo.
Yeah. I'm trying to. Okay, is that okay? You see it and and you hear me? Yeah. So, well, thank you. Since this is a panel, I only have 2 slides, so I'll be short. Let me time myself. Since this is a panel, let me just make a super, before my 2 slides, a super short comments about the previous speakers. I essentially agree with no objection with everything which has been said. I found very interesting, Vincent, points, I think very insightful, and his implicit criticism over an excessive sort of too naive taking of local beables, I think it's very good. It's very insightful, and I share his suspicion to taking local beables too strongly, not because they couldn't, the idea couldn't be generalized somehow, but it needs to be generalized in particular. And with respect to what Antony is saying, my reading of what Antony is doing, it's not doing interpretation of quantum mechanics. He's using interpretation of quantum mechanics idea to do physics. He's doing physics, not interpretation of quantum mechanics in a direct sense. So so once again, within his perspective of doing physics, I think it's clear what he says. My view of the time issue in quantum mechanics is much less vague. I think that situation of the confusion about time in quantum mechanics was a situation 20 years ago. I think there's no problem about time in quantum mechanics, in quantum gravity, if you do things properly, and now we understand it. And this also serves as an introduction to two things I want to say. As I said, I have two slides. This is the first slide. I hope it's not too small. The first slide basically is one point I want to make in general about space-time and quantum. And let me put it this way, very often, but not with the two speakers before me, very often I get nervous when I hear talking about space-time and quantum, because I feel that there's a lot of ambiguity in saying space and in saying time, both of them. And people talk as if space was something obvious, we know what it is, and we have to sort of understand how it interacts with quantum, or even more with time. But by space and by time, we mean very different things. And if we disentangle these different meanings, a lot of confusion goes away. And here is 5 different meanings. The first 3 refers to space and time, the last 2 only to time. One, and let me be precise here, because I think this is crucial. One is that by space and time, we might mean something very general, which is the notion of space that was universal before Newton. Namely, space is the order of the things, how are they located one respect to the other, who is next to whom, adjacency in Cartesian terms, or boundary in Aristotelian terms. That's a notion of space, spatiality. I mean, where is something? Is next to something else. Where am I? I'm in London, Ontario. Which has nothing to do with Newtonian space. Has nothing to do with metric structural space. Has nothing to do with a specific property of space in classical mechanics, and which remains valid in many theories, and might very well remain valid in quantum gravity. I mean, a black hole, it's a complicated thing perhaps to define and localize, but to say that I'm going toward inside the horizon it's something which is non-problematic at all. I mean, I'm next to the horizon or not. And the same about time. I mean, a local notion of time as counting a set of happenings, one after the other one, irrespectively of direction, irrespective of the metric of this, whether it's affected by gravity or not, is something that remains valid in all the from Aristotle to quantum gravity to loop quantum gravity theories that I'm aware of. A completely different notion is Newtonian space. Newtonian space, it's a very structured metric things in which things move, and Newtonian time is this metric independent variable, which is the preferred independent variable of the dynamics, and they are just a little bit modified in Minkowski space-time, but they have the same sort of metaphysical role in Minkowski space-time, and these when we talk about space and time in this sense, we're not talking about space and time in the previous sense, which is a relational notion. These are sort of entities which are there with respect to which other things are located, and we can use the Newtonian time, of course, as a counting way. We can use 2 as a way for organizing 1, but 1 is general, 2 is very specific. It's an idea by Newton, which works very well, but we know it doesn't work in general relativity. So 2 dies as soon as we use general relativity. So people who confuses 1 with 2, and that's one way of expressing also what Vincent was saying, confuse the fact that we can localize observables by being local in one sense and be local in another sense. So be local in a given metric or given external space-time is not the same as being local in a relational things. In a relational sense. And of course, 2 dies entirely in general relativity. In general relativity, what happens is that 2 disappears entirely. So there's no container of things. There is no manifold on which things happen. There is a gravitational field, and this gravitational field is in some approximation the Newtonian space, just when we disregard his dynamics. And the gravitational field can be used to, like other things can be used to define a notion of relative localization. Now, once we go to time, the same happened. I could repeat the same discussion for time, but there's more, because time has macroscopic, the macroscopic world is of course full of irreversible phenomena. So there's a preferred direction of time, there's the issue of arrow of time. And then of course there's experiential time, passes, flows, we remember the past. And this, I believe, are again, it should not be confused. When we talk about, and this confusion is, I think, coming out. Even when Antony says, I cannot use the time as time, the scale factor, because it comes back. And so what? I mean, what's the problem of coming back? Coming back, it's only a problem about irreversibility. And irreversibility is, it's something that appears, emerges only on the macroscopic level. And experiential time is only something that we can understand in terms of how the brain works, how we remember the past into an irreversible macroscopic world, and how we anticipate the future. That's the where we understand experiential time. And irreversible time, it's a thermodynamic story. It's not a story about mechanics, quantum mechanics. So it's just a recommendation. When you talk about space and time, whether it's related to quantum or else, be very careful, because everybody's talking about something different. And a lot of confusion, I think, is a mixing of these 2 things. Now, let me go to, that's very slightly here. Space-time and relativity notion are still there in quantum physics and quantum gravity. Newtonian time disappear entirely in quantum gravity. Quantum space-time is a quantum gravitational field. So quantum space and the process are not localized in space-time, but they nevertheless have a relative localization in space and time with respect to one another. Irreversible time is due to thermodynamics, statistics. There's no arrow of time in quantum mechanics by itself. I'm strong about that. I know that some people disagree. I think I'm wrong. And experimental time, we often confuse time in physics with things that happen in our brain. Now, second slide is the following one. And now we go to quantum gravity. And I want to make a key point, which is dependent on the previous slide. And it's related to both things that Vincent and Antony said. Now, in quantum mechanics, if you, in many interpretations of quantum mechanics, let me put it this way, if you want to talk about specific properties of a system that can be observed, that connect to what we observe, you have to break the universe in 2 parts, in sort of the system and the observer in Copenhagen sense, or the system with respect to which the previous system is variable, or in many worlds, it's only when you have a split of this sense that you have some of the variables here that take a value with respect to other one, which is there is a correlation. And this is also true in pilot wave theory in a more subtle way, in which I don't want to go here and discuss because it will take us long. So if you want take away pilot wave, it's fine for me. But it's definitely strongly true in many interpretations of quantum mechanics, and this breaking plays a crucial role in both Copenhagen and the relation of quantum mechanics and many worlds, because variables, values of variable are relative to another system. So this is called the Heisenberg cut, the famous Heisenberg cut, of course, which you can cut CUT, not CAT, which you can, which we also know you can move arbitrarily toward the right, not necessarily toward the left if you don't want to do something. So, in my opinion, this is what quantum mechanics talks about values of a system relative to something else. Now let's go to general relativity. In general relativity, things are localized. Of course, they're localized. A black hole is localized, but not localized with respect to a Minkowski space-time at some coordinates. It's localized with respect to whatever is around it. And we can talk, there is a notion of locality in GR. Everybody working in GR knows very well that there is a very strong notion of locality in GR, which is not locality with respect to the coordinates, x and t, of the Einstein equations, not locality with respect to the manifold, but locality with the dynamical variables with respect to one another, the fields with respect to one another. So given a gravitational field, I'm somewhere with respect to the gravitational field. Given a gravitational field of the Maxwell field, the black hole is somewhere with respect to the magnetic lines, and so on and so forth. Now, this is also a relational notion. A localized system is related to something else. Now, I do quantum gravity, and in the way I do quantum gravity, these two relationalism, so to say, Einstein localization, Heisenberg cut, are identified. And one is used for the other. So the way quantum gravity is done in loop quantum gravity, especially in covariant loop quantum gravity, is to describe quantum phenomena, quantum space-time phenomena, happening in a region as they affect the surrounding space-time. So imagine that this red region is a star collapsing, going through a quantum transition, exploding in a white hole, and coming out in the and in between there is no space-time. In between there is a quantum superposition of space-times, if you want. So what the theory gives you is probability amplitude given what you observe in the past to what you observe in the future, of what you observe in the future. Or more precisely, let's not talk about observations, given values of the gravitational field and the matter fields somewhere, values of the gravitational field and the matter fields somewhere else around the region. So the Heisenberg cut between the quantum system and the system with respect to which the system the values take value is identified with the Einstein cut, which are localized things with respect to one another. Here, clearly, it's being used a relational notion of space and time, right? So the one of the previous transparency is not being used anything like Minkowski space or a local beable in the strong sense in which team modeling interprets Bell, for instance. Yeah, unless we have a previous space-time where things are localized, we don't know what we're talking about. Of course, we know what you're talking about. Average relativistic knows what he's talking about when he says a black hole, Sagittarius A star is a black hole and is the center of our galaxy. It's there. It's not somewhere else. Okay, but not there with respect to space-time, with respect to the galaxy. So exactly this notion of relative localization can be used to have local, in this sense, observables, which connect a quantum region with the surrounding. I've taken my 15 minutes. I'll shut up. Thank you very much.
Thank you. Okay. Good. So I will let Vincent and Antony to say something about each other, Carlo. And of course, Carlo can reply to anything, and then we open the floor to all the participants.
I just have a very quick comment about these notions of adjacency and surrounding space-time at the quantum gravity level. Why do you want to keep with these spatial-temporal notions, which might be problematic if you consider superposition or these kind of things? Maybe because the key thing in your description is the relational components. That's the thing you want to take from quantum mechanics and general relativity and bring together in quantum gravity. So why not go for a kind of generalized notion of relational entities at the quantum gravity level, which need not especially be adjacency or surrounding these kind of notions, but in terms of I don't know. I've suggested, or people have suggested, entanglement, for instance, as a kind of new world-making relation, for instance, at the quantum gravity level, because there are quantum theories. So what do you think about this kind of more radical approach in a sense, and then having kind of these spatial-temporal notions being reconstructed or emerging out of these more fundamental relational structures?
I find they're interesting suggestions. I'm puzzled by them. I see something similar happening in loop quantum gravity, because the quanta of space themselves, when they're adjacent, they are intertwined, they are entangled. So one wants strongly to think this way. But I think that there is a well-posed question, which is on the basis of general relativity as it is and quantum mechanics as it is, can we make sense of a quantum theory of gravity? I think the answer is yes. And we have examples, more than one. And so this is a possibility for a picture of quantum gravity, a picture of space-time consistent with GR, some limit, and consistent with quantum mechanics. That's good enough for me somehow. And then the question is that, can we understand things deeper? Can we go farther? That's different questions. I think quantum mechanics as it is, namely one thing attaching to something else, is sufficient. And if you want, why? Because of locality. The great discovery of 20th century physics is that interactions are local. So some sort of locality should be there, compatible with entanglement, compatible with the rest. But locality means that to interact, you have to be close by. You have to be nearby, right? So to measure, you have to interact. So to measure, you have to be nearby. And there is a sense in which you're nearby in loop quantum gravity, because the quanta of space are located one with respect to other one. And so it seems to me you can build a quantum theory of gravity on what we have already. I'm not against exploring these ideas, but I'm not convinced why they're necessary.
Okay, Antony, do you want to say something? Okay, just open. So I have from before Hippolyte, Guido. So if Hippolyte, you want to, and then we're gonna have Nicolas and Eric.
Yeah.
And whoever wants to ask a question, just write the name or.
Okay, thank you. So it's a question on relational quantum mechanics. It's not really dealing with quantum gravity. I just wanted to ask Carlo, what was the nature of the cut in relational quantum mechanics? Is it purely functional, or do you think it has some kind of, I don't know, epistemological flavor or whatever? And another really quick question is, so I'm really appealing to your interpretation, and I struggle to see some kind of, I don't know, to me it seems kind of, because I like it, so it's quite flawless to me. So do you have, I don't know, some kind of, I won't say weakness, but do you think that there is some kind of open question or stuff that you would like to clarify yourself, or some open question you would like to answer on relational quantum mechanics?
Thank you for what you say. The first question is what is the role of the cat CUT? Is that
It's nature, yes, because it's not ontological. It's completely universal. You can put it everywhere. So who is putting the cat actually? So how do you decide to put the cat or not? Do you have some kind of reflection on it?
It's a great question. Thank you. In a sense, it's the same question as the same question is in Copenhagen quantum mechanics, right? Where you can move the cat far away from the system. It seems to me that this is just functional. It's completely arbitrary. It's not physics. Wherever you consider how in any way you imagine breaking the world, the degrees of freedom in subsystems, it's always true the rest of the story. That seems to me. I don't know if there's more than I can say about that. There's something similar in classical theory as well, right? I mean, the world can be described remarkably. The world can be described by breaking it apart and making it in components which are not. It's not total reductionism. When we describe a pendulum, we're not describing its atoms. It makes sense as an object, and it's well described. Of course, at any cat, there is an approximation. And that's one of the ingredients of the story. You're disregarding something. The second question, I have an open question about which in my mind I keep going around, which has to do with the Renner question before. Namely, suppose I want to be super realist, and I want to say that God sees what everybody sees. Okay, so God knows about all relative variables at some time. Can I? The answer is yes, because why not? There is nothing contradictory. There's nothing logically contradictory, provide, of course, that it disentangle the probabilities, because otherwise we go to the usual end, provided to violate locality badly. Locality is always some version. So, we violate locality not just in the way the Bell inequalities violate localities. The violation will not the Bell locality, but much more stronger somehow. The one that comes into the. So in a sense, relational quantum mechanics has two versions, if you want. One is that well, okay, let's put together all the views of all observers in a big bunch, and that's God's view. But then it's horribly non-local and so on. And the others just don't do that. And you can just not put things together, and then you have a decent locality and so forth. I've been oscillating between these two views. I don't know which one I prefer.
Okay, thank you very much.
Okay, Guido?
Yes, thank you. I mean, this in fact follows on very nicely from what you were just saying, Carlo. I wanted to ask you whether, in fact, your recent work on stable facts has any implications on how you see locality or the treatment of EPR in relational quantum mechanics.
Yes. Yes. Well, the locality is it's a delicate, as Guido, you know very well. It's a delicate notion, right? You can define locality in a number of different ways, and there is a sense in which quantum physics is non-local. Okay, period. Period. I mean, there's anybody who says no, it's local, it's just wrong in that sense. Okay, because of EPR. But it's a very weak notion of right. There is a sense in which Bohmian or pilot wave quantum mechanics is non-local, which is much stronger than that sense. So it's more local, more non-local than what just the phenomenology of and so I think this is true in in relational quantum mechanics, if you are in a deep quantum regime, and I think this is the question that you're asking, with respect to everything, every single observer thinks are local, but that's too weak because of course they're local. They're just whatever arrived to him. But then there is the semi-classical approximation, which we understand because of the coherence and stability, which give us a coherent picture of the world, where, however, there is this violation of this Bell violation of non-locality. So I don't have much to add to this picture here. Strictly speaking, you know, from the perspective of relational quantum mechanics, if I'm here and there is the other EPR couple down there, with respect to me, nothing happened. Okay, so it's not that there is spin up or spin down. There's nothing. There's neither. And the correlation only manifested when information from there gets to me, and then is non-local. There's no violation of locality, and vice versa. Seen on the other hand. So this is the way in which relational quantum mechanics saves a level of locality which it's acceptable and allow us to understand why there's no we cannot send information faster than light, but it doesn't take away the breaking of a local world that Einstein would like either, of course. So you can use the coherence, you can go to stable fact, and then you see that something is it's missing. You cannot construct a completely stabilized world which is local. Is that an answer to what you were saying?
Yes. I mean, it helps.
Thanks.
Now we have Nicolas.
Okay, thank you. Yes, let me maybe start with at least an observation which I believe is relevant to today's discussions. We started this morning with Renato Renner explaining at length that if we assume that they are quantum agents, we run into a contradiction. And then we had Philippe Grangier, who reacted strongly and shortly saying that doesn't need to be proven because it's obvious. Then I have to say I had to leave, so I missed some of the talk this morning, but this afternoon I was back and I listened to Antony and then to Carlo. And at least from my understanding, we were talking about wave function of the universe, and we were talking also if it is obvious that we are quantum agents, and it is that obvious that it goes without saying. So it seems that there are those for which the existence of quantum agents is obvious, and those for which the non-existence of quantum agents is obvious. And would be nice to talk about that and find out. So at least Renato has an argument, which I personally find very convincing. I mean, my talk yesterday also made it clear that I don't believe in quantum agents. But it's not sufficient to assume that the answer is obvious. So maybe this is provocative and it goes to all of you, and including you, Vincent, because I didn't hear your opinion on that. I probably already know the answers from the two of us. So maybe we can discuss about that. Are they quantum agents?
Good. So who wants to start?
Did I misunderstood you, Antony? You're assuming that they are quantum agents, and this is so obvious that you don't even need to mention that.
So I'm afraid I wasn't able to listen to Renato's talk. Was it this morning, I think? So, but I mean, I followed a bit of this debate. I mean, beginning with the original. When did the paper come out? A few years ago. The one about this that there's no the experiment, the sort of extended Wigner's Fraukiger and Renner paper.
Yeah.
Now I mean, well, maybe I can just say a little bit of history. What, you know, with that paper, I mean, I saw it on the archive when it came out. 2 people wrote to me asking me what I thought of it. And one of them was Lee Smolin, and the other I think was Carlo, or was Simon Saunders, who CC'd Carlo. Anyway, listen, I mean, the paper had just come out, and I wrote back saying, look, I thought that there's just, you know, from a de Broglie-Bohm point of view, if you take into account the fact that there is an empty wave here lurking around, you know, there's no issue. It will all go through, even though I hadn't really looked through the details. I had a little exchange with Carlo and Simon Saunders. I think Carlo agreed with me. Anyway, and then a year or 2 went by. I think it took a long time for the paper to be published. It eventually got published in Nature. And then a student of mine said, look, there's this paper. And I said, look, it's just the empty wave. And then he said, why don't we write something on this? So we started going through the paper. We were writing up something, and we'd almost finished it. And then on the archive, there appeared a reply. I don't remember their names now. There are a couple of philosophers who wrote a paper showing that, look, you know, if you include the empty wave, you can explain all this in terms of de Broglie-Bohm. And the point is that you just have to be careful about assigning wave functions to systems. Now, I didn't see any problem. And so, of course, my student and I, we didn't bother finishing our paper because basically, that's it. Lazzarovici and Hubert, I think that's it. Thank you. You know, I thought that they'd just basically express what we wanted to say. So now my feeling is that this question, whether this Frauke Gerenede scenario, is it interesting or is it not interesting? It probably depends on what your view is about quantum mechanics. You know, I think from a de Broglie-Bohm point of view, it just doesn't seem too interesting. But I can understand that from other points of view, maybe it is interesting.
Maybe, Antony, just a very quick, are we, you and me, quantum agents? Yes or no?
So sorry, when you say quantum agent, you mean?
Does quantum mechanics applies to us?
Do you mean that an external observer could apply it to us? So, okay.
Maybe in superposition, can someone measure us and find a measure in a superposition state, whatever, as we can do with qubits?
So I think that, I mean, okay. So if you ask me from the point of view of de Broglie-Bohm, then I would say that yes, in principle, we're quantum agents, everything, but you have to take into account the fact that there are empty waves lurking around, which could complicate things.
And Carlo, what is your opinion?
Well, I think that Renato's work is very clear. And first of all, it's clearly right if you just go into details. But it makes very clear that it has a strong result based on some assumptions. These assumptions, one of, if you in the context of this discussion, pilot wave theory violates one of these assumptions. The version of locality. It's not just the locality of, there are other interpretations that don't violate the locality asked by Renato in his theorem.
I think his assumption about locality is what people usually call no signaling. So it's a very weak form.
Yeah, that's right. That's right. Sorry for not being precise with my terminology. Yes, that's right. So pilot wave. If you go to if you take seriously the ontology of pilot wave, which I think is perfectly possible and consistent, then you violate that hypothesis of Renato theorem. Renato can confirm that probably. So there's nothing mysterious about that. I mean, it's in pilot wave theory, you have an ontology where you have an observer. Of course, the observer can be in a superposition in the sense that his wave function it's double, but he's just one of the two branches because the flesh observer is not in one or the other. And how do you circumvent Renato's impossibility of absolute facts? By just violating locality.
But so according to you, not according to Bohmians, I don't think you are Bohmian. Okay, maybe you can contradict me here. are we quantum agents? Yes or not?
Yeah, I think we are quantum objects. According to me, we are just quantum objects like, well, according to me, we are quantum objects. We are objects. All objects are quantum. Facts are relative to us and like they're relative to one another. But of course, when we interact, if I interact with you, you can measure aspect of me and be in a situation at some point in which you're, with respect to the facts, with respect to you, you cannot use the fact that I am that the variables describing me have necessarily one value or the other. With respect to you, I don't have a fixed position and fixed velocity.
Okay.
Okay, we have a follow-up by
Could I maybe
Marco
just
and
add?
then-
Sorry, could I just maybe add a brief thing that,
Yeah, go.
that might be helpful? You know, I think from a De Broglie-Bohm perspective, you know, if you just ask the question, in what circumstances can we apply textbook quantum mechanics? Then, you know, there are some conditions that have to be satisfied. You have to be in quantum equilibrium. That's one thing. But one thing that I think it tends, which was there in Bohm's papers in 1952, which tends to be not remembered, is that you have to have a situation, in order to recover standard textbook quantum mechanics from De Broglie-Bohm theory, you have to confine yourself to a situation where, when a measurement takes place, basically the empty branch of the total wave function stays separated from the branch that you're in, that it doesn't come back to re-overlap. Now, Bohm gave an argument in his 52 papers saying that, look, if you include interactions with the environment, the chances of the different branches re-overlapping, they would have to re-overlap with respect to every degree of freedom. And it's as unlikely as, you know, putting a kettle of water on ice and it boiling. There's kind of argument, which maybe someone should look at that in a bit more detail. But so I think that this is relevant to the Renner-Fraukiger business. That, look, you know, can you apply quantum mechanics to a system? Well, from the De Broglie-Bohm point of view, really, there is also this point that, hang on, you have to assume that you're not going to re-overlap empty waves. Yeah, so
okay, I will stop here, but it would be fun to hear Renato or Philip or maybe.
I mean, maybe I can just, I would like actually maybe to just confirm what Antony just said. So it's true that you could take the argument as an argument essentially in, I mean, you can always say if some interpretation violates one of our assumptions, and of course our claim is that the assumptions lead to a contradiction, then our claim, our kind of no-go result could be seen as something in favor of that interpretation. And now in the case of the De Broglie-Bohm theory, what happens is indeed what Antony essentially explained very well, I think, that an observer or an agent is not allowed to use quantum or textbook quantum mechanics to an outside system under certain circumstances. Of course, in real life, these circumstances don't usually occur. But of course, the thought experiment is just constructed in such a way that the conditions under which that, according to Bohmian mechanics, have to be satisfied that an agent can apply textbook quantum mechanics to the outside world are not satisfied. So I completely subscribe to that. I would not call, I mean, there's no talking about locality or non-locality, but of course, it's kind of implicitly there. So what really happens in some way is that if I, for example, prepare a spin and send it, let's say, to Carlo to measure, and if I prepare it in the spin-up state, according to Bohmian mechanics, it could still happen that he gets the outcome down, despite the fact that I prepared a spin-up state. It's just, I mean, this can happen because the way the whole thing around me, the other wave, the branches of the wave functions were prepared are such that this flip happens. Of course, this really contradicts textbook quantum mechanics, because I would say that's, I mean, obviously, if I prepare a spin up and send it to Carlo and there's no interaction, it should measure up. But this is what's happening. So in that sense, I think what was said before is, yeah, I would completely confirm that. But I would not call that a violation of a non-locality assumption. I would say the assumption that is violated is really the assumption that we can apply quantum mechanics from an agent's perspective to the outside world. And I think maybe the question I would pose back is, what is really the, let's say, experimental evidence that we could ever have? Because all our experiments were, of course, done from a perspective of an observer. So in some way, we are taking a theory which was developed by making local experiments from my perspective, from our perspective, and never from God's perspective. Nonetheless, we are somehow interpolating this and saying, now let's take this as the correct theory from God's perspective, so to speak. And that I find personally a strange step, but this is more, let's say, a philosophical argument against quantum mechanics, that the way a theory should be developed, in that way, in that process, it's strange to make the step from essentially evidence, which clearly takes us as the observers to say, no, this is actually not the ultimate correct thing. We have now to make this flip and say, this is actually the correct thing from God's perspective, and the other thing is sometimes not correct. So that's, in my opinion, a very, let's say, I would say,
on that,
not highly non-obvious step to do. Yes.
Well, look, in theoretical physics, there's often this sort of tension between, people on the one hand who want to, let's look at what we see and what we can measure and control and work from there, and then there are other people who will sort of introduce some kind of speculative structure and use it to understand things. There's always this tension, and you need both, really. I might say that, for instance, if we think in cosmology, according to current cosmological models, there's much of the universe in a modern cosmological model is in principle unobservable if all you can see is on the backwards light cone. And yet we're used to, maybe wrongly, but you might argue, but we're used to just assuming that, look, that's what our theory tells us about the world. There's this region out that is, it's space-like separated from us that is there, and in some cosmological models, you'll never be able to see those regions. Arguably, it's a little bit like that with the empty wave in de Broglie bone. But I think it's a fair question. You can ask, well, is it really credible? Should we, which theory is better? I wouldn't want to dismiss querying this. But I would just wanted to say really that I think this kind of thing is quite common in theoretical physics. That's all.
Just a very quick finger on this, maybe.
Yeah, of course.
I think just to answer now Nicolas' question, I think it's pretty clear that according to this general understanding of quantum agents in relational quantum mechanics of Carlo or Bohr mechanics, then we are a quantum agent in this general sense. I think the answer is pretty clear. But I think Renato then clearly put the problem, so to speak, it's kind of discrepancy or gap between the behavior of the physicist in the lab and then the description of the real situation according to the theoretical framework of Bohr mechanics, for instance. But this is, there are other instances of such a gap as Antony just mentioned.
Okay, if Ariane want to follow up on that, and then we move to the next question, which is Christian, and then we have Weidmann after Christian.
So it will be short because it's related to the work of Renato, and we had discussions about Bohmian mechanics concerning his experiment proposal, and I think it's very interesting to realize that there already the idea of David Deutsch that you mentioned about the fact that you can have a memory of something, and an observer can have a memory of something, but not too much memory, because otherwise you have kind of rich path information which will break the coherence of the full quantum states. And all the trick of proposed by Renato Renner is to use a kind of RD experiment. So the famous experiment with showing a non-locality, and also it was a big discussion concerning Lorentz invariance. And this experiment, when you consider this non-perfect entangled system, and you introduce observer inside of the language of the framework, then you get an apparent paradox, and which is solved only if you try to understand that all the point of view of the observer can only put together in one good way if you have a common agreement between all these point of view. And it was the aim of my different questions later, before with the talk, after the talk of Carlo Rovelli, is exactly this problem. You have different observers and you can decide to put all of them in one common picture, and this is the Bohmian mechanic in my way of thinking, or the Brightbaum theory. Sorry, but yeah, there's no really problem, I think, in that point of view.
Okay. Any reply by the panelists on that? Okay,
maybe just a comment.
Yeah, go.
It's just more or less to confirm what has been saying. It's nothing I disagree. I was very much confused about pilot wave theory. In fact, at some point I got, I even thought it was wrong. And the reason is that to make predictions with pilot wave theory, if you see the particle, think it's just a particle in some position, you should know the wave function. Otherwise, you cannot make prediction. But the wave function, you cannot see it. So how can you make the standard prediction? How do you describe laboratory? And now there is an answer, and there's a clear answer. So I worked out the answer. The exercise that Antony said somebody should do it a little bit better, inspired by what Bohm says in his paper. And the answer is the coherence. Namely, if you measure, I don't know, speed up or something in the laboratory, and think in terms of not the full quantum wave function, but the relative wave function, which makes sense in the body Bohm, and you the coherence, then the standard calculation of the textbook quantum mechanics makes sense. So this is what Antony was saying and Renato was saying, namely the actual prediction of textbook quantum mechanics with respect to one observer and one system are only true with some conditions, which is that the empty wave doesn't come and make damages to what you're predicting. And this is always realized. This is largely realized in our laboratory precisely because of decoherence. So I think in Bohmian mechanics, coherently, like in most interpretation, in many interpretations, every system it's a quantum observer, but nevertheless, in that sense, it's true. But the predictions, the standard prediction of quantum mechanics are only true if you are in some approximation, which in Copenhagen it's clear, because in Copenhagen you ask the observer to be macroscopic, so you're implicitly folding in the coherence.
Okay, good. So Christian?
Yeah, I'm supposed to go next, but I don't want to ruin this very nice momentum with this conversation. So if there are people that want to ask some, because I wanted to ask about some other topic. So if you have questions about or closer to this, I can wait.
Just wanted to say thanks, Carlo. I agree with what you said. That's all.
May I just? I was very surprised.
If you have a follow-up, yes. Okay, good.
Yeah, I was very surprised that Carlo didn't jump when somebody said that according to relational quantum mechanics, we are quantum agents. Clearly, I don't know. I'm not in the EPR correlation with any spin. I cannot know both spin up and spin down of any spin. I think clearly we are classical objects because we understand only classical concepts. We are only in one position. Of course, we are quantum objects. In all this interpretation, everything is quantum, so we are quantum. But we think in classical terms. And so Nicolas' question, if we are classical or quantum, clearly we are classical objects described by quantum mechanics. And maybe again, I'll push Carlo again. Maybe, usually, as I understand it, the definition of the coherence is when you have systems and they in touch with environment, and environment measures them, and this is the coherence. If you have a macroscopic object or microscopic object interact as they're supposed to interact, this is not the coherence. And Carlo, you said in your interpretation, and Bohm interpretation, and any other interpretation, that the coherence is very important. And I think it's not important at all. The fact that things become entangled with environment, it's maybe important when we perform some quantum experiment and we have to work very hard to make the interference. But explaining all our behavior of macroscopic objects is completely unnecessary. In the moment we are macroscopic, interference is not feasible anyway. So the fact that we're entangled or not entangled with environment makes no difference whatsoever.
So I'll only answer slowly, rapidly to the first part about we are classical, we are quantum. The suggestion of relational quantum mechanics, which is different than the suggestion of pilot wave, which is a different take on that, is that there's a common language. Classical and quantum is not classical nor quantum, and the common language is the following. The systems, they have variables. These variables take value at some moments, in some situations, and that's what we're talking about. It's the same in classical and in quantum. So a pen has a position, I have a certain height, my mouse a certain color. The variables in which we describe systems. The difference between classical and quantum in the relational perspective, this is specific relational perspective, is that in quantum mechanics, in classical mechanics, you assume that these variables, all the variables of all the system always have a value, and this value is just absolute. So this is black, period, and is always black, whether this is interacting or not. This is incompatible with quantum mechanics. Unless you restrict the set of variables as you do in pilot wave theory to a commuting algebra position. And the reason is because of the theorems like Kocher-Spencer. So in relational quantum mechanics, you assume that these values are only realize that in the interaction, they actually mean only what happened in interactions, are relative, and always one respect to the other. So there is not a question of what is classical, what is quantum. Everything is physical. Everything is it's coherently described by the values, the relational values of quantities. The coherence plays no role at all. The only role of the coherence, it's connecting this very relational picture with a curiously non-relational picture of quantum mechanics. And to do that, you need the coherence of classical mechanics. So only in the classical limit, you use the fact that so you lose interference in the way we know.
Okay. Nicola asked about agent. In particular, you are agent. Are you consider yourself as a quantum agent?
Yeah, like if you make measurement on me, you can see interference if you're good enough.
I'm not Wigner. Clearly, I cannot make interference with you. And do you yourself in a superposition? There is a meaning for you being in superposition. There is such a thing. In many words, there is no such a thing like I in a superposition. It's not. It's forbidden by language. There is no cat in a superposition. All macroscopic objects are well localized. So in your situation, humans can be in a superposition.
There's no language in relational quantum mechanics about being in a superposition.
Exactly this what I wanted to say. Therefore, you're classical agents and not quantum.
Maybe just a point, Lev, it might be helpful just to, for instance, in the context of Bohm mechanics, the notion of quantum agent as used in Renato's thought experiment is not fundamental. So you have a unified, from a fundamental or ontological perspective, there is no difference between classical systems or classical agent and quantum agent, if you want. But the notion of quantum agent as captured in this thought experiment is not fundamental in the Bohmian picture. So in this sense, in a general, from the Bohmian perspective, we are quantum as quantum systems as any other.
Bohmian
But not in this.
Bohm made everything classical. You have well-defined position of everything. According to Carlo's definition, a position of everything is well-defined. In Bohmian mechanics, everything is all agents are classical. So it's
or quantum, because you have a universal description. You call it's a verbal matter. Call it quantum or classical. It's just the same if you want.
It's not the same. Bohmian, everything is classical. And I thought that Carlo is kind of more flexible, and he didn't jump the things that there might be quantum agent. He has this. I know this spin knows. If it's an EPR situation, it knows both sigma x and sigma y. So this is clearly quantum. Bohmian cannot be like this. Bohmian has
but I mean, the Bohmian particles do not have classical trajectories in a certain sense. Depends what you call classical, or I mean, but this is a verbal dispute. It's not relevant. The important point is that there is a unified description, which includes what you call quantum agents, but which does not capture the features of the quantum agents of Renato's thought experiment, because they are not relevant in the Bohmian perspective.
Okay, maybe since there are just 20 minutes left, we move to the next two questions by Christian and Davide. And then if there is still time, we go back to the issue of the quantum agent. So Christian?
Yeah, I actually, my question, I wanted to go back to the presentations and the roundtable, the topic of the roundtable. So I think my question is sort of inspired by what Vincent has said, and is directed to Antony and Carlo and whomever in the audience knows about quantum gravity. And so my point is, I liked what Vincent was saying about this idea of having these metaphysical views that can help us, a philosophical view like monism, that can help, or holism and so on, that can help us understanding some part of quantum mechanics to make them more systematic from a philosophical point of view. I know that nobody is, not everyone is moved by these ideas, but some of you are. And one of these sort of philosophical approaches that have been developed, and this is what I like, is that this is sort of largely interpretation independent. So these views are based on features of quantum mechanics that are supposed to or are largely independent from the interpretation. And one of those that I like particularly, which is also the one I used along with Claudio, I was there, to sort of provide an understanding of relational quantum mechanics, is this idea of indeterminacy, according to which there are values of physical quantities, either at the fundamental level or at some emergent level, that are not fixed, that are not definite. So this is a very metaphysical sort of idea. But since it is largely interpretation independent, I believe, I was wondering whether we could expect it to be found also in theories that are quantum, but not quantum mechanics, so like especially quantum gravity. And I want to know this from those who are working on this theory. And I have only one small example, which I'm not going to be able to fully and entirely like reconstruct, but I remember from a paper from by Carlo and I think was Speziale, about the minimum length. And I remember that Carlo was saying something that I really enjoyed, namely that if an observer measure a minimum length, then another observer is going to, it's not going to find a sharp value. And this was sort of something that some bells ringed in my head, connected to a similar approach to superposition states in quantum mechanics, using exactly this idea of metaphysical indeterminacy. So again, very shortly, I want to ask if you have another example, or if there are approaches to quantum gravity that might have similar examples. Thank you to anyone who replies.
I am completely sympathetic with your notion of indeterminacy. I think, in my opinion, is the you know, I said at the beginning of my presentation that each interpretation of quantum mechanics asks us to renounce something which we hold dear, and then give us wonders about a lot of other things that in other interpretation we don't like. This is definitely true for pilot ways. It's also true for many worlds. Many worlds is a remarkable interpretation of quantum mechanics. Each one has some costs. The cost of the relation interpretation, but also the step that the relation interpretation says, look, if you accept this point, all the rest come through. It's exactly indeterminacy. So the idea that there are some values of variables, some variables that genuinely have no value at some time for some system. You know, when the spin Lx is up, the spin Ly just, there's no meaning in it. Why? Because the spin Ly is just a description of how the atom interacts with the magnetic field in the y direction, so to say. And there's no magnetic field in the y direction, so there's just no way of that. That's somehow, it seems a very different way of thinking than de Broglie-Bohm, but it's not such a different way of thinking, because de Broglie-Bohm, you say, well, the velocity, forget about the velocity, forget about the momentum as an observable. The momentum is just something which is defined in terms of position. It, of course, it's a different way, but it's a in de Broglie-Bohm, you just throw away half of the Dirac variables. In relational quantum mechanics, you keep all of them, but not all determinates at the same time. So indeterminacy is what disturbs a strong notion of realism. But if you, the message of relational quantum mechanics is if you accept indeterminism in the sense of your paper, then so many other things like you know, locality and a weaker form of realism and so on goes through.
Okay.
Thanks.
Okay, if Antony and Vincent don't want to add anything, Davide?
Yes, thank you. So I have one question for Carlo, but then I will profit to have a follow-up on the coherence, what Lev was saying. The question for relational quantum mechanics is this one. So maybe this question doesn't make sense in the relational context, but just to understand it better, once we have an event that this is a relational fact, it is in the ontology of the interpretation. My question is, what happens between facts? What happens, sorry, between interactions? So take for the classical case of double slit experiment. I send an electron, goes through the slit and then hits the screen. Now, what's the story between the source and the screen? Okay. Then if there is time, I can also make my follow-up with the classical limit story, but that's a question I wanted to ask to Carlo. That's important.
Well, it's the answer is it's what just Christian said, is we don't have a story. There's no story. I mean, there's no meaning of the story. That's it. Of course, there's no meaning of the story, which doesn't imply that there is some physics going on there, which is which is unrelated to anything that that correspond to what affects me. And then, as I mentioned before, nothing prevents me to think that there are plenty of things that happening there. It's just not variables which are relative with respect to me. And if I try to make a story, I make a non-local story. Non-local in the strong sense, non-signaling. Yes, signaling story. So in a sense, you say, you're pointing, the first paper of Heisenberg, which started all that, the 1925, before Bohr, is, Heisenberg came back and wrote to his friend Pauli, it's not yet clear, but the electron doesn't have a trajectory anymore. There are facts that happen, and forget what happens in between, and we're going to understand nature better. I think relation quantum mechanics, let's take this seriously and see if we can make sense of that.
Okay, it may be close to a stochastic way of thinking about the dynamics.
Yeah.
Like you have just discrete events at random times.
Yeah. Which is Bohr intuition, by the way. Bohr, Max Born intuition. Born intuition was that down there, the discrete events, no space, no time. That was his intuition. Just discrete quantum events connected in a probabilistic way.
Okay, thank you. Thank you very much. If I have time, so I don't know if I misunderstood before the discussion what Weidmann was saying about the coherence, but I mean, the point of the coherence is that there is no quantum classical boundary, so what we have discovered is that there is no macroscopic object which is classical because it's macroscopic and a microscopic which is quantum. Everything is quantum. Then at a certain point, quantum systems that are strongly coupled with the environment becomes classical, but this story is within the quantum formalism. So the idea is that I'm well localized because I'm classical. That doesn't work. This is exactly what the coherence tells us. I mean, we should make this clear. And in Bohm's theory, it doesn't make sense to say Bohm's theory is classical because there is a particle there. Now, Bohm's theory is a pilot wave theory. There's a wave function that plays a role. And the story of Bohm's theory and the Everett interpretation within the decoherence approach is pretty the same. Once you have a unitary evolution of the wave function, the way you couple with the environment, you have a diagonalization of the density matrix and a description of pointer states is exactly the same. The only difference that I see is that pointer states become branches in the many words interpretation and the effective wave function in Bohm's theory. And that's why in Bohm's theory, the coherence is related to the measurement process. So I wanted to make clear this point because I thought there was some misunderstanding here.
Yeah, I agree.
I don't know. Should I just clear my point? The point is that at least definition, the standard definition of the coherence is like you said, that you have a interaction with environment. And all people say that this is very important for many words, and Carlo says it's very important for his interpretation, for everything else. And I say it's a mistake. In the moment you have macroscopic object, this macroscopic object, you don't have technology to make interference. And the only important thing is that we cannot make interference with macroscopic objects. So we don't need environment. So it's not the coherence. So you can have things which completely isolated from environment and perform all kinds of quantum experiments, but in the moment they're macroscopic, you don't, then you have, maybe if you have what you need for the coherence, not ability to interfere. But really nothing was entangled. You're still in pure state, in pure A plus B and whatever. So this was my point. And Carlo repeated the coherence so many times. And Wallace says you cannot have many words without the coherence. And this is what I'm trying to, this is a myth of quantum mechanics, which I was trying to
I mean, you can say that, but from the point of the coherence, it's wrong. As a classical object, you are mostly entangled with everything that interacts with you, with light photons, with our molecules, with everything.
Of course, in real life, there is a lot of decoherence.
You're not a pure state. You're never a state.
If I will put some super intelligent, super Wigner, which will prevent this entanglement with environment, I will not see any difference in my life. So the coherence is this decoherence is not important. It's happening purely.
Okay.
I don't say that there is no decoherence. It just say you don't need it for explanation.
Okay. Any comment from the panelists on that? Otherwise, Paul as the question. Next question. Okay, Paul.
I was thinking that maybe it could be argued that all of these ontologies are incomplete because they don't take into account phenomenal character or what it's like to experience green, you know, the qualia, like the greenness of green. I was wondering if maybe they could comment on that.
I have a comment about that. And I think that it's mixing different problems. Qualia and the stuff are related to different sort of problem. What happened in a brain like mine, and the complexity of the brain and all that stuff. I'm not saying that this is not an interesting problem. It's a very interesting problem, and I have some sympathy for some direction of solutions, less from others. My own opinion is that mixing that with the physics of the atoms is it's a mistake. We understand physical object in terms of physical objects, and this has nothing to do. So the Wigner direction, it's just completely wrong. It's misleading of where the kind of solution has. Perhaps the other way around. Perhaps if we interpret physics relationally, then maybe we have a better sort of general, if we go that way, perhaps, I don't know, we have a better general philosophical approach where it's easier to think in terms of relation. So instead of just my brain state is related to something else, but not in the direction that anything related to our mind and psychology and experience, phenomenological experience, help us to understand why an electron passes through two holes at the same time.
I was just wondering if ultimately
that's an opinion, might be wrong.
Yeah. I was just wondering if ultimately an ontology should include qualia in your opinion.
Just a very quick comment on this.
Yeah.
Maybe I think it's a good strategy in general if it's possible to keep separate the difficult issues of the immersion problem or the ontology of quantum mechanics and the mind-body problem. They might be related, I don't know, but as a start, I think it's a good strategy to try to keep them separate, right? Because there is no reason to expect that things will get easier if we put them together. But
okay, so we started a bit late, so we have some time more. I have the last question by Alberto, but if someone else wants to ask a question, now or never. So Alberto, please go.
Well, thank you. Just wanted to make a comment on the matter of the coherence, yes or no, and see what the panel thinks about it. And is the following. If you look at a laser beam in air, that's actually a coherent state of multi-particle system, and air decoheres the laser. You can see it with the eye, okay? But when you do a spectroscopic experiment, an ultra-high vacuum, the experimental physics knows immediately that more the vacuum is good, the better and the faster you get the quantum statistic for your quantum precision measurement. So there you know that the coherence doesn't matter. So what I'm trying to point out is that there are different problems and different matters at hand, and they tend to be confused. And maybe one of the reasons is that because there is no detailed description of the processes. that are satisfactory for at all levels, the question whether the ontologies are complete or not is maybe relevant, maybe not from the point of view we heard before, but it is a relevant question. Would be curious to hear from the panel. All the three, if you have something to say, please.
Antony, sorry, you have an independent question, or you wanted to answer? We cannot hear you.
Hello, sorry, I'm seeing you say we have a bit of time. I just wondered if I might ask a sort of historical question regarding Carlo. It's a different topic.
Okay, can we just ask if you, the panelists, have something to answer to Alberto's question first?
I'm not sure I've understood exactly the question, Alberto.
Let me repeat it. So there are physical processes where you can immediately observe the role of the coherence.
Yes.
Processes where you have a multi-body state, like a laser, you have a complex order parameter, is a multi-body phenomenon, and so on. There are cases where the coherence is clearly not important. The example I made.
Yeah, what was the example? That's what I missed.
Is that when you do an that's experimental physicists in spectroscopy, for example, unsatisfied with the coherence. Why? Because when you do the experiment, the more the vacuum is made, the less atoms, the less agents of the coherence are there, the faster and the more precise is the measure. And there's a quantum measure, and so there you know that the coherence not only is not relevant, but if you take it away, it works better from a quantum perspective. So what I'm trying to point out is that maybe the question of the coherence is relative to the problem at hand, and that the coherence theory does cover the first example, but does not cover the second.
My understanding is that the coherence is a fact in some situations. I think it's not a theory in a sense. It's just something that happens in some cases, which we can describe when there is some loss of quantum coherence due to entanglement with something that we don't control. And it's helpful for answering very specific questions. It's not needed a priori for something. And the very specific question is why we don't see interference between this and that in concrete cases. So it's a fact. It's true in some cases. We can estimate, we can do calculation to see what's the amount of the coherence, and it tells us why certain interference terms become invisible. I don't think there's anything mysterious in the coherence. It becomes mysterious if you try to use it as the basis of the interpretation of quantum theory. Then you say, well, wait a minute, it's not sufficient. It doesn't give this, it doesn't give that, probably. But by itself, I think from the experimentalist point of view is correct. You're saying there are cases in which it doesn't apply. I would say in some sense it applies always, because look, take the simplest case. You have an atom, a radioactive atom, and you have a Geiger counter, it clicks. Good, there's no decoherence there. Well, if I use a Schrödinger, if I do a Schrödinger calculation, the wave arrives continuously on the atoms. Why there isn't interference between the part of the wave that arrived before and the part of the wave that arrived later? Well, because the detector is classical, so in principle I could invent an experiment like that, but I should have to find interference terms in the superposition between two different clicking on the Geiger counter. This is cancelled by the fact that the thing is microscopic. So there's nothing I disagree with you. From a theoretician point of view, you're always using the coherence in the moment in which you actually state, all right, this is the outcome of the measurement out of the probability thing. You're just assuming that you're not seeing from now on, there is no way to measure interference between other outcut or measurement. Are we saying the same thing, or are we saying something different?
I think for the example you made, I can see how you can try to put the coherence in. But for ultra-high vacuum spectroscopy, I really believe that what one observes is that the more you take away the decoherence agent, the better and the faster you get the measure right. So you really have a situation where this kind of reasonment don't work because you don't have a theory to describe what happens through the measure there. There's no big deal, but who does the experiment every day? It has the opposite intuition.
Ah, yes, I see what you're saying. Yes, of course, yeah.
It's exactly the opposite.
Yes, yes. Well, because you want to measure quantum effects. So in a sense, to measure a quantum phenomenon as opposite something which is described classical, you have to take away the coherence. I see the point.
But then there are cases where it's not important. Not all.
Okay, maybe
cases.
I don't see a contradiction.
Okay, maybe we make just one last quick round of the from the panelists, starting from Antony, who had a question, and then.
So, Carlo, I just wanted to ask you about your views about Heisenberg's version of quantum mechanics. I know you've been looking at some early papers. So, in your talk, I was just reminded. So, when I did that work with Guido Bacigalupi on the 5th Solvay conference,
I remember.
So we found some interesting things about, if you look at the lecture, so Born and Heisenberg gave a joint lecture on what they call quantum mechanics. And it's amazing just how very different it is from textbook quantum mechanics. So a couple of things. I mean, they have sort of static states. I mean, the time-dependent Schrödinger equation is only for subsystems and so on and so on. But there was one thing in particular that I wanted to raise with you, is that they seem to have no collapse postulate. Now, they do have a discussion about, how do you avoid interference? So, I mean, let me give a specific example, which I think they discuss. I mean, it's going from memory now, 10 years ago, and we were working on this. But let's say you have an atom that's in a superposition of energy states. And let's say we measure the energy. Now, in sort of modern textbook or Dirac version of quantum mechanics, well, the quantum state collapses to an energy eigenstate, okay? What Born and Heisenberg say, and they say this very explicitly, is that, look, I've got this quantum state, it's a superposition of different energy states. When I measure the energy, I still have a superposition. But what happens, each term in the superposition picks up a phase, and these phases are randomly distributed. And if you think about this, if I have, think about the density operator, if I had a statistical mixture of superpositions with random relative phases, it has the same, I mean, they don't say this, but it's something that we discuss in our book. Is that how you get the same density operator as if I had a statistical mixture of energy states? So in that sense, it works. But their postulate, instead of having the collapse postulate, their postulate is if I measure energy, there's no collapse. I just create this randomization of the phases. And funnily enough, this is repeated in Heisenberg's textbook of his book of 1930, The Physical Principles of the Quantum Theory, in the appendix, which is quite technical. He has the same thing. Curiously, I mean, just to finish this story, curiously, in Bohm's book, I mean, what I find amazing about all this is that no one ever talks about it, but in Bohm's book of 1951, his textbook on quantum theory, he has the same thing, and he generalizes it to any observable. If I'm going to measure an observable, I expand the quantum state in terms of those eigenstates. When you make a measurement, I don't get a collapse. I get each term in the superposition picks up a random phase. That is what's in Bohm's book, amazingly. Now, funnily enough, Guido and I don't know if Guido is still here, but we were trying to follow this up. But it turns out that, so Bohm, as we understood it, learned his quantum, probably got this from Oppenheimer. I mean, the evidence is that Oppenheimer at Princeton in the 1940s was still teaching this. And Oppenheimer, probably, he had spent time in Göttingen with Max Born. So it seems that, you know, this thing that's there in 1927, Born-Heisenberg, Heisenberg is still saying this in 1930. It seems that Born taught this in Göttingen, and Oppenheimer got it from Born and was still teaching it at Princeton in the 40s, and it's in Bohm's book. And it's amazing, and nobody ever talks about this. I wondered if you had some comment, if you thought about this, or...
Guido, do you want to say something before?
Is Guido here?
Yeah, I'm here, but no, I don't want to add anything. Actually, now that you say it, I can't remember exactly having seen it in Oppenheimer's lectures, but yes, definitely in Bohm, and it's in Heisenberg's Chicago lectures.
We had, let's say, circumstantial evidence that Bohm must have got it from Oppenheimer, must have got it from Born. And I remember you went and dug out Oppenheimer's lectures.
Yes, I dug out Oppenheimer's.
We were going to look at it, and we never got around to doing it. But...
Yeah, my memory is that he doesn't explicitly.
I see. Okay. But it's certainly there in Heisenberg in 1930. I mean, Carlo, what's your view of this? You're saying that you seem to be saying in a sense that you think that, you know, Heisenberg was doing quantum mechanics properly, and then Schrödinger came along and messed things up a bit. So what about this aspect of what Heisenberg was doing?
Yes. So 2 comments. First, Antony, Guido, you're much deeper and better historians than me, and you know the evolution of this field much better than me historically. I'm not historians. When I mention these things, it's not to make an historical point; it's to make a point relative to the to what I think are current problem today. So whether I am exactly representing what I read in the papers, whether they correspond exactly what all these people had in mind, I don't know, and I let you to say that. So my point was that I don't know what Heisenberg had in mind exactly. You seem to know it better than me. And I take your point. I believe it, of course. The point I was making is much simpler. If you just take basically the Zur Quantenmechanik 1 and Zur Quantenmechanik 2, you with insight, that's it. You can do all calculations you want about no relativistic quantum mechanics from there. Perhaps adding some our experience later, and maybe taking away some of the ideas which these people had. So I don't know whether this other curious aspect of the way of thinking is that of the projection that you're saying is I didn't see in those papers, but you're not saying it is those papers. You say it's in later in the survey discussion. So I don't know, but. The only strong point I want to make is that there is a way of thinking of quantum theory where the only meaning of state is sort of the entry of the transition amplitude, what one would call preparation in the quantum information language. Or one of the label of the roles of the matrix mechanics matrices, and so my point was more rhetorical, and of course Schrödinger theory is great. It's not, but we can think about quantum mechanics without thinking about the wave function ontologically. That was the main point of my talk. Only that.
I mean, if I may add, I think that's at the back of Heisenberg's mind. That because the wave function is not ontological, I mean, you can use the sort of standard form of the collapse. You can use this kind of dephasing, as long as you can calculate the right probabilities out of it. It doesn't really matter what the state is. I think that's in the back of Heisenberg's mind there. I mean, that's my speculation.
Okay. Well, we are late, but maybe we can go on a little bit, and then so there's Alberto, and then there's Wayne. Maybe Alberto, since you already spoke, shall we give the word to Wayne first?
It's actually a question about what people were just talking about this historical point.
Go Wayne.
Okay. Yeah, so Antony and Guido, I find it interesting that you say that, because I was looking at the history of the collapse postulate a little while ago, and the earliest version of it I could find was from the Heisenberg Chicago lectures. So I just interested if you guys know of an earlier version of it. And the interesting thing is there it's quite explicitly a postulate on the lines that Carlo was talking about. He says the mathematical representation changes discontinuously because our knowledge changes discontinuously. So he's clearly not thinking of it as an shift in the ontic state of things. But like, is anyone explicitly say, well, look, after a measurement, you replace the state with a new one earlier than that?
So I think isn't it the case, Guido? Am I misremembering that in the Solve and the general discussion, doesn't Dirac basically say this? I mean, Dirac gives a little, it's a few pages. He gives you his view of quantum mechanics in the general discussion at the end of the conference, and it reads like a sort of thumbnail sketch of modern textbook quantum mechanics, isn't it? There?
Yes, I mean he does. Yes, he does say if we sort of expand the wave function in a certain way, then we have to consider that nature chooses one of the components. That's also in the general discussion at Solve. But a sort of systematic formal description of collapse. Von Neumann has it in November 1927. Now that's the paper in which he treats sort of quantum mechanics as a statistical theory to his satisfaction from his point of view, where he proves what later came to be known as his no hidden variables theorem. That's the first sort of systematic discussion of collapse.
So von Neumann's got it already in 1927. Von Neumann's got it already in 1927. Okay, I'll look at that. Yeah. It's an interesting thing. It's not in the first edition of Dirac's principles. I think it shows up in the second edition, the jump.
Okay. Wayne, can I just question and comment? I mean, you brought up Heisenberg's Chicago lectures. So that's the book, The Physical Principles of Quantum Theory, right? Because my recollection, and again, it's having read it decades ago, it may be that in the body of the book, he says something like that sounds like the collapse postulate. But if I remember rightly, in the technical, I don't know if there's an appendix or there's some kind of chapter at the end of the book, that's where he gives the technicalities. And the discussion there about how to avoid interference in energy measurements, it is based on this, or at least as I could understand, this kind of randomization of phases. And I wonder if maybe what you're seeing there is that in his view, what's really going on is the randomization of phases, and then it sort of looks like there's some kind of collapse. But I mean, I think the impression I had at the time looking at it is that he thought that what was really going on was the randomization of phases, and there isn't really a collapse. But
I think it's clear he doesn't think. I think it's clear he doesn't think that like the collapse is some kind of physical process. right? So I mean, I've got right in front of me. He says the mathematical representation of the physical process changes discontinuously with each new measurement. The observation singles out of a large number of possibilities, one which has actually happened. And as our knowledge of the system does change discontinuously, the observation, its mathematical representation must also change discontinuously. And it says that's to be found in classical statistical theories as well as in the present.
So there's a question about updating knowledge, but I think the sort of thing I'm talking about is about how do you avoid interference?
Right.
And there, the example he gives with an atom, I think going through some sort of interferometer, you know, it's the randomization of phases, and it's very similar to what Born and Heisenberg have in their Solve lecture. By the way, is that cat behind you dead or alive?
Quite alive.
Even without you observing it.
Yes.
Okay, Alberto, you want to add something?
Thanks, Antony, for the comment on the random phases, and remind, if it's helpful, that David Bohm was the one to introduce the random phase approximation in the study of electronic properties of solids, just in the same years, just before he wrote the 51 papers were published. So yeah, it's interesting. It's interesting because it connects to his view of early decoherence ideas.
Yes. Okay.
Thank you very much.
Okay, that's going to be the very last question by Paul. Unless, and of course, after I think that the room can be open, so I mean, people are open, they can stay. But anyway, Paul, we cannot hear you. Paul.
Hi. Quick question about relationalism. If Alice measures an electron and gets X spin up, then if Bob measures Alice, he's guaranteed to get the fact that Alice got X spin up with probability 1. But that would seem to meet the EPR criterion for reality. So does that push back on relationalism or no?
Can you repeat the last phrase? Does this push back?
Does it push back on relationalism if it means that
No.
It means...
that's why we see a coherent world. I mean, it's there's a lot of coherence in a general sense in the world we observe. The point is that there is also some incoherence that comes up when in complicated situation where Bob measures spin up and then Alice measures spin in a different direction. So it's not that every single observable has a completely different picture of the world. There's a lot of coherence between what goes on. The point is to account whether the things subtly don't match in the way Renato is pointing out.
Okay, but does Alice, according to Bob, does Alice have the property before Bob measures?
No.
Does it mean
no, the set of values relatively to Bob don't change unless there is an interaction between Bob and the system.
So does that mean the EPR criterion is wrong? Because he's guaranteed to get a spin.
Probably yes. Think about that. I think yes. What is?
Okay.
It's wrong. It doesn't apply to nature.
Thank you.
Okay, so on this note, I'm gonna give back the floor to Christian for the last remarks. And well, thanks for the to the panelists. And
I really don't have remarks. Just thank you, the chair and the panelists and everyone. And we'll see you tomorrow morning, some of you, or tomorrow evening. Ciao.
Bye-bye. Ciao, ciao. Bye-bye. Thank you.
Bye.
Thank you, guys.
Bye. Thank you.
Bye.
Antony,